Good morning, all. It's a pleasure to me to introduce you today Dr. Boutheïna Kerkeni from Tunisia. She obtained her PhD at the Paris-Meudon Observatory in France, and then she spent 8 years in UK, first in Oxford, for 5 years, and then at the University College in London for another 2 years, and then she was back to Tunisia in 2010, and she got the position of full professor in 2015, and she's the head of an active research group in theoretical chemistry from 2011 there at the university, and she's an expert in theoretical chemical methods like quantum chemistry methods like initio, DFT, but also in molecular dynamics and the study of collisions and gas reactions in the gas phase, but also at hybrid interfaces. And she is visiting us at the IEC for 6 months with a program that is called Science by Women of the Foundation Mujeres por África. And she's working in our IEC group, and she's now working with the theoretical simulation of mid-infrared spectra of complex organic species like fullerene derivatives in order to have reference spectra to search those molecules, for example, with the James Webb Space Telescope. And today she's talking about complex organic molecules in the interstellar medium with a particular focus on some species that are relevant for the formation of amino acids. So.
Okay, thank you, Anibal, for this introduction. And I will start to acknowledge the fellowship by the Foundation Mujeres por África that is giving me this opportunity to foster collaboration with Anibal and Ransel by investigating new aspects related to complex polycyclic aromatic hydrocarbon materials. And today I'm going to talk about the quantum chemical paths and the kinetics of formation of propyl cyanide and acetaldehyde, which are two molecules detected in the interstellar space, and for which we do computations to predict the reaction paths, the feasibility of the species that lead to their formation. And we study this on the surface of dust grains. First of all, let's have an overview of the discovered molecules that are reaching more than 200 species so far. And they are detected via rotational transitions in the microwave, millimeter wave, and also nearby the terahertz region. And this has demonstrated investigation of interstellar matter. So these species can be molecular, radicals, or ions, and more than 70% of them contain carbon. So the majority is organic. And there is a large fraction exceeding 30 molecules that contain the cyano group, which is very interesting for chemical species related to amino acids, etc. And many of these detected species are biological molecules or prebiotic, which means that they will lead through different recombination to biological molecules, and are detected so far in protostellar clouds, in star-forming regions, comets, meteorites, and planetary atmospheres. And the purpose is to understand the chemical processes that led from atomic or diatomic molecules to recombine and to lead to these huge molecules, the complex organic molecules, which are mainly organic, and they are composed of more than 6 atoms, so we call them complex organic molecules. And this might shed light on the processes that led to the origin of life on our planet Earth. So the first molecule I'm going to introduce in this presentation is the propyl cyanide, 3 carbons, 7 hydrogen, and CN group that I had talked about earlier. It has the particularity of being the only molecule detected in the interstellar medium that has branched isomer. So here I show on this figure the branched isomer. Here it's called iso-PrCN, so that the CN group is here bonding in the middle of the carbon-carbon-carbon chain. This isomer was detected in 2014, while the straight chain isomer called normal propyl cyanide, which is composed of two other conformers, the anti and the gauche being more stable here. And they were detected with ALMA towards Sagittarius B2 with a ratio of abundance of the isomer over the normal of 0.4. So this link with the amino acids, the shape of the branched isomer, led too much interest into studying this its formation. What are the species that will recombine and will lead to its formation in these extreme physical conditions of the interstellar medium? So very low temperature and very low pressure. So far no calculations have been done in the past, but several observations are still focusing on this sort of branch type molecules in the same cloud of forming stars. So what we have come up to is to choose our ice model. So the grains in these dense clouds are covered with ice layers. The ice can be composed of many species. Accreted species can be carbon monoxide, whatever. So we took the simple. So we make simple. This is the water cluster that we choose. It has been prepared by other theoretical methodologies. It's composed only of water molecules. And upon this ice model, we have started reacting species. So many questions can rise here. How does the chemical species form in space? What are the configurations in space that will lead them to encounter to lead to the formed detected molecule? What are the formation routes? Are there energetic barriers or are there diffusion barriers? What are the processes that will allow them to meet and form? So basically, our choice of species here is radical based. So we choose radicals. They were insight from the observers that also use some kinetic astrochemical modeling, and they have already proposed to study these association reaction between, let's see here, methyl group CH3 with this species, or CN group with this species here. All of them were detected in the same cloud, and they lead to the iso conformer, the one that has the branched shape. And also there are three other possibilities of recombination of radical CH3 with this species here, C2H5 with the C2CN, and also CN attacking the carbon on the side here to form the normal, which is called the straight propyl cyanide molecule. So we have considered these recombination reactions. So far in the kinetic modeling by astronomers, they were using energies and details about these reactions from previous simpler reactions. So there is a need to use quantum chemistry and kinetics studies to provide appropriate and specific parameters for each of these reactions that can be used and can lead to the diagnosis of the cloud physical conditions, its temperature, column density of the species, etc. So we can have a firm decision about these physical quantities. The computational tools are the following: the electronic structure part, which uses the basically good treatment of the electron interactions in a molecular system. Here we have molecules mixing together, or radicals, let's say, more accurately. And the second part is the kinetics. So we are interested in computing rate constants. So the rate constant is the speed of which a reaction occurs at a given temperature. And these are important because they are directly linked to the intensity of the emissions that are detected. So if we have a rush rate constant, then we can definitely be confident of what are the species that are detected. And the different radical associations that I have introduced so far have been then computed with the electronic structure calculations, which gives us on the vertical axis here we have the potential energies of the electron distributions versus the carbon-carbon approach. So we are approaching radicals here, right? And we are varying the carbon-carbon distance. And what we see here on each figure, I have shown the radicals that are associating. For example, to form the iso-propyl cyanide, here we have CN, the carbon in CN approaching the middle carbon of the other molecule. And this is at large distance, so they've separated the radicals. And as far as the carbon-carbon distance gets closer, we form at the equilibrium here, the equilibrium distance, RE, we form the isopropyl cyanide, the molecule that is observed. And it's the same for the other associations, and also for example, the normal straight chain propyl cyanide. The CN group is in this example approaching on the side of the carbonaceous skeleton here, and as soon as the distance reaches the equilibrium, it's around 1.5 angstroms, we have the straight chain propyl cyanide formed. And all these potential energy, electronic potential energies, can be given by an analytical function, which is very useful for astronomers, so they can just take the parameters that were fitted to get these shapes, and they can apply it for each of the associated radicals. And of course, these potential energy curves will govern the speed of which the reaction occurs. And here I show for each of the 5 cases that we have seen earlier, the rate constants that I have talked about earlier versus temperature. And here we go from 10 Kelvin up to 300 Kelvin, spanning the range from dense to diffuse clouds. And we see that the reaction in both cases, either isopropyl cyanide or the normal rate chain, we have the CN addition is the one that has the largest rate constant. So for both isomers, the addition of the CN group to the other species has the largest rate constant. But overall, all reactions, as they are barrierless, it's a characteristic of radical-radical association, the rate constants are decreasing with temperature, and all the channels are open anyway. And we have fitted for each of the cases the rate constants, the numerical values, to this Arrhenius-Kuit expression, where we have to look each time when fitting to the alpha, beta, and gamma parameters that here I quote in this table for each of the reactions, and where I highlighted the most the reaction that has the highest speed, which is the CN, as I have mentioned before, for iso and normal. All the 3 other reactions, the H3 association for both cases, iso and normal, and also the C2H5 association reaction, have more or less the same trend and are lower in magnitude. So probably these values, predicted values, can shed the light to be able to run the chemical, the kinetic modeling of the cloud chemistry that are done by our astronomer colleagues. So to be able to predict from the model the right iso to normal ratio that was detected, 0.4 from the observation, so that they can extract the physical quantities relevant to the region where these molecules were observed, deep in the star-forming region, Sagittarius. Now I am going to move to the second molecule, which is acetaldehyde. It's a molecule. It has been observed since the 1970s. It is a precursor for biological species. So there are lots of processes that will occur using acetaldehyde to form glycolaldehyde or acrolein, and its abundance so far detected in space is around from 10 to the minus 10 to 10 to the minus 9 with respect to H2, and it has been observed in several environments like crystalline cores, translucent clouds, the Hale-Bopp comet, also in interstellar ices and meteorites. And here I am studying its formation on an example of an interstellar ice type. So far, the ice model types that exist in the literature are carbon monoxide-rich ices, for which no dynamical or kinetic studies have been done. Methanol-doped ice, for which the formation of acetaldehyde was only diagnosed in the case of acetaldehyde formed in an electronic excited state, which is not really of interest because the observations have shown that acetaldehyde was detected in its ground electronic state. So that's why we found that this study is of interest on this type, on this methanol doped ice. So here we have a methanol on the edge of cubic ice cluster. So here we have water molecules, and one of the edges has been replaced by a methanol molecule. So the model was already proposed in the literature, but as I said, the study was done towards the formation of excited electronic state of acetaldehyde, and here we look at the interplay between ground state and excited state, and we show what is the appropriate route to get acetaldehyde and to be able to explain the possibility of its detection with the abundance that is mentioned by the observers. So here I'm not going to enter too much into the detail of the graphs because these again are potential energy, electronic energy interaction of the different species versus the reaction coordinate. What I'm going to say here is that we start with carbon atom that is so abundant in the interstellar medium, and it's coming from its ground electronic state, and it's gonna meet with the methanol that is on the edge of this grain model, and a lot of reactions will occur, and some of them will occur on a triplet electronic state system, and some on the ground state. And we look at the ground state, and we show that there is an interplay between excited and ground state, and we focus on this part of the reaction paths, which is the rate limiting step. It has a very quite reasonable barrier around 10 kilocals per mole, and it corresponds on the to the CH3 dissociation from oxygen CH moiety here. So this is the energetic barrier that is here surrounded in yellow. So the CH3 detach from these species in order to link to the other carbon edge, and therefore acetaldehyde is formed. And once it's formed, it's adsorbed on the grain. So we see that the ice has been restructured. The shape of the ice has been changed from its initial shape here, when we started the collision, up to its formation. And the desorption of the acetaldehyde will require only 8 kilojoules per mole, which is really nothing with respect compared to the exothermicity of the reaction. The reaction, when it occurs here to form acetaldehyde in its electronic ground state, it is obtained with an excess of energy due to the reaction energy that has been obtained here. So in the end, we have acetaldehyde that is ejected into the gas phase, and the ice remains on its own. And this part of the reaction, the rate limiting step, is shown here in detail from the quantum chemical calculations. So these are really accurate calculations using highly correlated methods. We have a small system, not like the one we have seen in the case of propyl cyanide, where we have 34 molecules of water. Here we only have 7 waters, 1 methanol at one edge, so we can afford really highly correlated methods, and so we can get really very accurate values of the energy barrier heights, and from this we can use our kinetic modeling to get rate constants versus inverse temperature. Here we are dealing with reactions having an energetic barrier. For the case of propyl cyanide, there were reactions association of a radical, so reactions goes directly straight away to the product without any energetic barrier, so a lot of energy is following there. And the different curves that you can see here are with different methods treating the quantum effects, if you want, because here we have an energetic barrier, so we have quantum tunneling and this sort of things, and we can see them here at the very low temperatures, how the rate constants can be 5 orders of magnitude difference from when you don't treat any type of tunneling or quantum effects, and when you take into account all these quantum effects. So we have the red rate constant is the one characteristic of this acetaldehyde formation in its ground state. So with all these data, we are confident that acetaldehyde, following these reaction steps that we have shown, can be really observed with the abundances that have been quoted by our colleagues. And finally, I would like to mention some points that the detection is only the tip of the iceberg in understanding the underlying chemistry. But we need to answer further questions in order to be able to interpret these observations. What are the chemical species that we choose? How the species is destroyed? How long it lives? What are the conditions that? What are the conditions of the medium where it was observed? And the challenging point is to combine laboratory experiments with comprehensive chemical models and to provide databases with quantum chemical data that are appropriate for every single reaction, and not be using some adaptative parameters, etc. So in order to get a good description of the system under consideration. Some other possibilities for our system is to, in order to make the databases more richer and more complete, is to use other types of ice models. We know that different ices are existing in these media, different shapes also, or mixture of adsorbent on the water ice, and with different morphologies, can be amorphous. Most of them are amorphous, not crystalline. And also we can therefore update the reaction network, because the different reaction will not occur on with the same way on different types or chemical composition of the ices. So we will be encountering several challenges, and we will be deciphering what are the new routes for every type of ice, and then provide parameters and a more global picture to aid the astronomers in their diagnosis of the observation. And finally, I think I reached the end, and I thank you for listening.
Thank you very much for this nice talk. So, time for questions.
Thank you very much, Boutheïna. I have one. How many possible reactions do you consider when you start to study a system? I mean, do you consider a lot of possible reactions, and then you end with 1-2 possibilities, or you do some kind of a screening?
Well, it depends on the molecule that you want to obtain in the end. So here, for example, when we started with the methanol molecule on the adsorbed on the ice, the purpose is to break the carbon-oxygen bond here, because acetaldehyde is the following. We have carbon-carbon bond instead. So the point is to introduce a carbon there. That's why here the reaction was initiated by a carbon. And then you start by looking at the different paths, and maybe you by test and trial, you find that this reaction that you have chosen will not lead to the molecule with the let's say thermal barrier height. So then you forget about it and you look at other possibilities, or you say, well, this reaction route does not lead to acetaldehyde in this region where it was observed, because it's typical of low temperature and high barriers will not be overcome for acetaldehyde to form. But for the case of the other species here, propyl cyanide, these association of radicals have been already guessed by the observers. So they were in their model, they had a nice model and a cloud model, and inside they were putting accreting molecules, CN the most abundant. So the majority of what I have here, and they expect them to recombine. But they don't have any specific parameter, neither for binding energies, desorption energies, or diffusion barriers. In this case, we see that because they are radicals, there are no barriers so far, and the reactions are really straight away. All the channels are open, and we provide for this so nice case the kinetic and the whole model that shows how these molecules are really easily formed. So we are really happy to find such results when there are no barriers. We are really happy that this can explain the abundance of observing such molecules in these media.
And what finally happened with the iso versus normal ratio?
But that one we do not predict ourselves, but providing this data, maybe we urge our colleagues to do the calculation using these parameters instead, that are system specific. We hope that this will shed the light and unravel what has observed, and this way they can extract some specific physical quantities of the cloud where the molecules have been.
Okay, thank you very much.
You're welcome.
Thank you very much. This nice talk. So it's just a naive question. So you have a different model that you use, like the ICE model. You said you're going to investigate more model, different model, compared to what you are using. I'm wondering if there are already many models, ICE model, and if the result that the parameters that you find are different.
Yeah, every type of ice, the chemistry of the ice will affect the interaction with the incoming molecules you put on top of it, right? So maybe reaction or a route, that reaction path that is feasible for with a low barrier or without a barrier on pure water ice, it won't be on the CO ice, for example. Like the radicals, maybe they will bind and never get out of the ice, so they like to be absorbed, let's say. So, but we have to have a clear picture, a general picture, so that we have a complete set of data to model different kind of ices, and just varying the parameters for one type of ice to the other, and the different species that will recombine on top of it.
So it depends on the parameter that you want to look for. It's depends on the parameter that you.
What do you mean parameter? What?
The model that you are using.
The ice,
yes,
the type
ice
of
model.
ice. Yes,
it
will
depends
depend.
of if you are want to plot like a relation between the temperature or the kinematic?
Yeah, of course. The kinetics, the dynamics and the kinetics will depend on the type of ice. Absolutely.
And which one is the best for the moment?
No, for the moment, for every one of these molecules I have shown, I only chose one type of ice. So for propyl cyanide, I chose only water ice because that's what the observers mainly have mentioned. But there can be other species on the ice, so the chemistry of the ice cannot change. But in my calculation, I only started with this, and maybe in the future we can add in other parts. In the pure water, we can add CO or methanol or mixture of them, and see how the reaction can follow.
So then, let's thank again our speaker for the nice talk.
Thank you.
Just two reminders, please, all students come here to sign in, and we are all invited to have a coffee with Boutheïna at the cafeteria. Thank you very much.